I'd like to say a few more things about section 4.4 before going on to orthogonality in section 5.1. So let me begin by reminding you one of the theorems from section 4.4. This is 4.13. Suppose we're given m plus 1 distinct t values and any m plus 1 corresponding y values, then there's a unique polynomial of degree less than or equal to m which goes through those points. And notice that m is 1 less than m plus 1. And I just want to remind you the way we think of this as a linear algebra problem. We think of it as a minimization problem where you can actually get the minimum to be 0. And the way we do that is we take this matrix A, which is the m plus 1 by m plus 1 van der Waals matrix. And we let alpha be the matrix of coefficients of the polynomial we're looking for. And we're trying to solve the equation A alpha is equal to this vector y. And the key point is that A is invertible. That's a key property of the van der Waals matrix. And you conclude that this vector alpha is A inverse applied to y. And then the polynomial that you're looking for is alpha 0 plus alpha 1 t plus dot 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 alpha m t to the m. Okay, that's just a refresher of something we did last time. So let's just think about what's involved here. One of the sort of complicated things that you need to do is you need to compute A inverse, where A is the van der Waals matrix. And that's not the end of the world, especially with a computer, but there's actually a more direct way to do this, which is quite important. So I want to say what it is. It's called Lagrange interpolation. And this is a way of solving the problem that I just mentioned directly without using matrices. And so I'll remind you that what we're given is these points t1, y1 to t m plus 1, y m plus 1. And we're looking for a vector alpha such that when you let f of t be this polynomial, then this satisfies f of ti is equal to y I. That's just to remind you, that's the problem that we're interested in. And rather than solving it using the van der Waals matrix, I'm going to solve it using the method of Lagrange interpolation. And it's a very clever trick, which goes as follows. Basically what you want, you first try and do the following. Find a polynomial. Let's call it pi, such that pi of tj is equal to 0 if j is not equal to I, and pi of ti is equal to 1. And of course, I should have mentioned the degree is supposed to be less than or equal to m. So this is actually a special case of Lagrange interpolation, where you're given the points t1, t2, ti up to tm, and the polynomial that you're trying to approximate is 0 at every point, except you ask that it be 1 at just a single point. So that's a special case. And it's actually fairly easy to find such a polynomial. How do you do it? Well, how do you make a polynomial that's 0 at all of these places? Well, what you do is you take pi of t is equal to, I want it to be 0 at t1, so take t minus t1. And you also want it to be 0 at t2, so take t minus t2, and so on, all the way up to t minus t I minus 1. Now, you don't want it to be 0 at ti, so I'm going to skip that one and put in t minus ti plus 1 all the way up to t minus tm. What does this polynomial satisfy? It's 0 at all of the points except for ti. And what's its degree? These ti's are fixed. And how many terms are there here? There's, sorry, I forgot the m plus 1 here. There are m plus 1 terms, except that you've dropped one. So the degree of this polynomial in t is equal to m. If you look, the leading term of it is t, 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 and so on. There's a t to the m at the beginning. Now, what's its value at ti? Well, it's not 0, because when you plug ti into all of these things, you don't get 0. It's some number. So we're almost there. We've got a function which has the proper values everywhere except possibly at this point. In order to give it the correct value at that point, you just have to multiply this by some constant. And, well, what you do is you divide by ti minus t1, ti minus t2, and so on up to ti minus tm. Right? Because if you plug in t is equal to ti here, all the way down to here, then all of these terms are equal. All of these terms are equal. And when you do that, when you calculate pi of ti, you get 1. Pretty clever, huh? Well, we're almost there. So write down these polynomials, p1 of t, p2 of t, up to pm plus 1 of t. This is m plus 1 polynomials, all having degree m. And if I add up these polynomials, let's write that down, p1 of t, and I'm going to leave a space here, p2 of t, plus dot 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 up to p n plus 1 of t. What kind of polynomial would this be? This polynomial would be 1 at t1, and all the other terms are 0, and 1 at t2, and so on, up to 1 at tm plus 1. This polynomial would be 1 at each ti. Well, I don't want 1, I want these fixed values, so I just stick them in here, y1, y2 to ym plus 1. Then this polynomial, if you look at t1, you get y1, and all the others are 0, and when you plug in t2, all the terms are 0, except here you get y2 times 1, so you get y2, and so on. And that's it. So the theorem is that this polynomial that we're looking for is this one here, y1 p1 of t plus dot 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 ym plus 1 p m plus 1 of t. Okay, so let's just stare at this for a moment and see what I'm saying. So these y1 through ym plus 1 are some fixed numbers. And these p1 through pm plus 1 are some fixed polynomials of degree m plus 1, depending on the ti's. So you put this whole thing together, it's kind of complicated, but this is a polynomial, degree center equal to m. And the coefficients, so in other words, I can write it as alpha 0 plus alpha 1 t plus dot 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 alpha m t to the m, some alpha i's, where alpha I is some complicated expression of the given data, which is the e's and the y's. And, well, when you unwind this, the terms get all mixed up together, so it's a rather complicated expression, but in this form it's quite simple. So I'll do an example of that in class, or you can look at an example in the book, which is example 4.17. That's all I have to say about section 4.4. There are a couple of other topics in the section which I'm going to omit, in particular the stuff about approximations in function spaces, and I'm going to go on to Chapter 5, or orthogonality. So we've already talked about orthogonality. Let me remind you. V is a vector space with an inner product, and we say that two vectors are orthogonal, of course, if their inner product is 0, and this is modeled on the familiar case of Euclidean space Rn with the dot product, in which case this corresponds to the condition the cosine of the angle between the two vectors is 0, which is to say they are perpendicular or orthogonal in the usual sense. Now in this setting there's an important concept, which is the following. Now, suppose we have a basis v1 through vn of a vector space. Then you say that the basis is orthogonal if all the vi's and vj's are orthogonal, if vi vj is equal to 0 for all I and j. Well, not quite. Obviously, if I is equal to j, then this can't be. So for all I not equal to j. And second of all, we say that this basis is orthonormal if it's, first of all, orthogonal, and second of all of these vi's have length 1. And in other words, you can capture both of these, and condition B is the same thing as saying that vi vj is equal to 0 if I is not equal to j, and 1 if I is equal to j. And it's worth parsing this word just for a moment. Orthonormal means orthogonal. Ortho means orthogonal, and normal means normalized, so that the length of each vi is equal to 1. And of course, there's an essential example of this. In some sense, the model on which this is built. The key example is Rn in usual Euclidean inner product, and you let EI be the standard basis, that is to say EI is the vector with a 1 in the ith place. Then this is then the vectors E1 through En, the standard basis of Rn, is orthonormal. Right? Because it's clear that what is EI, EJ? Well, if I is not equal to j, the 1's are in different places, so you get 0. Whereas if I is equal to j, the 1's are in the same place, so you get 1. Well, so one obvious question is to look for other examples of orthonormal bases, in particular in Rn, or maybe in other vector spaces with an arbitrary inner product. But let's start with a very simple example. Let's do R2 with the dot product. So we've already seen that the standard basis is an orthonormal basis. But let's find another one. And, well, let's see. How do you find a basis? Let's just find a basis and then worry about whether it's orthogonal. So to find a basis, you start with any vector. So let's start with some other vector, say 1, 1. Now, we want an orthogonal basis, so for a second vector, we better choose something orthogonal to this. So let's take 1 minus 1. Well, there you go. There's an orthogonal basis. 1, 1. And, excuse me, let's take minus 1, 1. And that's a right angle. So if you call this V1 and V2, then V1 and V2 is an orthogonal basis. Now it's not orthonormal because the length of V1 is the square root of 1 plus 1, which of course is the square root of 2. But remember, if V is any vector in a product space, then you can normalize it by dividing by its length. Then this vector has the norm of this vector V over norm of V. We've already seen is the norm of V over the norm of V, which is 1. So all you have to do is take another vector. W1 is V1 over the square root of 2, and W2 is V2 over its length. And these are still orthogonal because all I've done is scaled them. And they're also length 1, so W1, W2 is an orthonormal basis. So you see that it's quite easy to find orthonormal bases. First of all, you just have to find orthogonal bases, and you can sort of build those up one vector at a time. And this rescaling takes care of the normality business. So let's sort of formalize this a little bit. There's two basic facts that are at play here. So the first one is suppose you give me m vectors, v1 through vm, which are orthogonal. Not necessarily a basis, but they're orthogonal. Then if you replace them with the vectors v1 over its length, shoot, that's not what I meant to say. Well, there's two basic facts at play here, which I'll now formalize. So the first is, suppose you give me a orthogonal basis of a vector space. Well, then you can easily get an orthonormal basis just by scaling v1 through over the length of v1 up to vn over the length of vn is orthonormal. So that is to say, it's enough if you're trying to construct an orthonormal basis, it's enough to just find an orthogonal basis and then normalize it like this. And that's let me draw a picture to illustrate what's going on here. All I'm saying is if you have, say, two perpendicular vectors, if you scale them, they're still perpendicular, and you can scale them so that they have length 1. That's pretty clear. So I'll leave that at that and go on to the next property. There's another basic principle at play here, which I'll now describe. Suppose you have m vectors in a vector space, which are orthogonal. So vi, vj is equal to 0 for all I not equal to j. Then this set of vectors is automatically linearly independent. And that's quite nice because sometimes checking linear independence can be a bit of a pain, but in this setting it's easy. And the reason is, well, if you draw a picture, it's sort of clear. If you have 2, for example, orthogonal vectors, well, they're pointing in different directions. And then if you had a third vector pointing in R3 off, that's in yet another direction, and so on. They point in different directions, so they're linearly independent. But let's give a more formal proof than that, because it's quite easy. What does linear independence mean? Linear independence means that if you have a linear combination of vectors, of these vectors, which adds up to 0, then the only way you can do that is if all of the CIs are equal to 0. Well, how do you prove that? Suppose you had some combination of these vectors which was 0. What's its length? What's the length of this vector? Well, let's compute the length squared, so I don't have to carry around a square root. The length squared is the inner product of C1 V1 plus CM VM with itself. And what is that? Well, when you take the inner product, one of the terms that you get is C1 squared, the length of V1 squared. That's from this term. And you also get C2 length of V2 squared and so on. Excuse me, C2 squared. Cm squared, the length of Vm squared. And there are a bunch of other terms, V1 paired with Vm, for example. But all of those other terms, the pairing is 0. So that's what it's equal to. And, of course, all of these numbers are all positive. And these numbers are all positive, and so the only way that can be equal to 0, well, if these vectors add up to 0, then the length of this vector is 0. And the only way that can be is if all of the CIs are equal to 0. So that's easy to see. So in particular, if suppose V has dimension n, then suppose you have n vectors which are orthogonal, all the VI VJs are equal to 0, then this is an orthogonal basis. And secondly, the V1 over the length of V1, if you normalize them, you get an orthonormal basis. So what that says is, in order to find an orthonormal basis in an n-dimensional vector space, basically the main thing that you need to do is find n orthogonal vectors. Let me conclude briefly with a couple of nice properties of orthonormal bases. So suppose we have a vector space with an orthonormal basis, which I'll write as U1 through UN, and U stands for unit, meaning it's supposed to suggest that these are of length 1. And then there are various computations in this vector space which are simplified. So, for example, suppose I give you a vector V, any vector. One of the things I could ask you about V is find the CIs such that V is equal to C1 V1 plus U1 through UN. And another thing I could ask you is, what's the length of V? And in the setting of an orthonormal basis, these are both pretty easy to answer. And so let me tell you how it works out. Well, the answer is, first of all, that the way you find CI is you simply take the inner product of V with UI. Let's see, what do I mean? So that is to say, I'm giving you some formula for this inner product. I'm giving you the vector UI. I'm giving you the vector V somehow. Well, you know how to compute their inner product, and then that gives you the CIs, which is to say V is equal to V U1 V1 plus dot 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 V UN UN. Excuse me, I keep switching to V's. V is this particular linear combination of the UIs. And the second thing is that the length of V is simply, well, let me write the length squared, the sum of the squares of the CIs. Which is to say, it's the, I'll just write it in another form, it's the sum of the V UI squareds. And let me just tell you briefly why this is true. Let's look at one. Why is this true? Well, if V is C1 V1 plus dot 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 CN, excuse me, U1 UN, we know that V can be written as some linear combination of the UIs. And once you've done that, if you take the inner product with UI, what you get is C1 U1 UI plus dot dot dot. And all of these terms are zero except when you get to UI UI. And right, so to calculate the inner product of V with UI, you write V as this sum. And then you expand it out, you get C1 U1 U1 UI plus dot 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 CI UI UI all the way to CN UN UI. And all of these terms are zero except for this one, which this number is 1, so this thing's equal to CI. And that gives you a formula. CI is equal to the inner product of V with UI. So that's this. And I'll leave the rest of this. Maybe I'll say something about it in class. I've gone on long enough already, and I'll see you in class.